Okay, Bismillah. Let's do this. Is reading chapter 3. I think I'm gonna be doing reading chapter 3 only today. Maybe some, I don't know, some exercises from problem sets too. I don't know. We'll do some problems. I don't know if we have time. Induction. Now that you understand the basics. Oh, wait. Should I read this before I watch the lecture? I haven't watched the lecture yet. Maybe I should read it, then watch the lecture. I don't know. Now that you understand the basics of how to prove that a proposition is true, it is time to equip you with the most powerful methods we have for establishing truth. The will-ordering principle, the induction rule, and strong induction. The will-ordering principle, the induction rule, and strong induction. These methods are especially useful. Wait. What are we reading? Propositions true. It's time to equip you with the most powerful methods we have for establishing truth. The will-ordering principle, the induction rule, and strong induction. Okay, so this is the most powerful methods we have for establishing truth. The will-ordering principle, induction rule, and strong induction. These methods are especially useful when you need to prove that predicate is true. Prove that a predicate is true for all natural numbers. When you need to prove that a predicate is true for all natural numbers. So we got natural numbers, okay. I think natural numbers are all the integers, positive or negative. Let's check. Natural numbers Natural numbers are the basic counting numbers used in every day. They consist of the positive whole numbers and go on forever. Depending on the math rules you use, the set can start at 1 or include 0. So not the minus. Only positive integers. Not physical. No friction. No friction or decimals. No negative numbers. The list has no end, represented by capital letter N. So there is no negative numbers, no negative integers. Okay, whole integers, whole numbers. Okay. Although the three methods look and feel different, it turns out that they are equivalent in the sense that a proof using any one of the methods can be automatically reformed. Although the three methods look and feel different, it turns out that they are equivalent in the sense that a proof using any one of the methods can be automatically reformatted so that it becomes a proof. Although the three methods look and feel different, it turns out that they are equivalent in the sense that a proof using any of the methods can be automatically reformatted so that it becomes a proof using any of the other methods. The choice of which method to use is up to you and typically depends on whichever seems to be the easiest or most natural for the problem at hand. The will ordering principle: every non-empty set of non-negative integers. So the wait sets, just because we missed, I didn't film sets on chapter 2. Sets are non-identical. How to say it? They can't be identical, like they cannot be 2 and 2. Let's check it just for your and my problem. Chapter 2, I did this reading without filming. I should have filmed. I should have filmed a lot of things I did, like my responsible design work that I did to get that certificate. Proof about sets. Sets are okay. Sets, I don't care. Sets informally, it's a bunch of objects. Well, this is sets. Are we talking about sets here? Non-empty sets. Yes, we are talking about sets called elements of sets. On point, the conventional. Wait. So sets, I think there is no notion of element. Wait, expression. Sets, I think it can have identical. Wait, there's something that cannot be identical. The intersection, different, complement of sets, cardinality. Wait, this is sets. What are we talking about? Proofs about sets. The sets, the set of all subsets of a set. It's called bar. Okay, sequences. Yeah, sequences. Sets provide one way to group a collection of objects. Array is a sequence, which is a list of objects called terms or components. Short sequences are commonly described by listing elements between parentheses, example A, B, C. So those are curly, sets are curly parentheses, and this is parentheses. So this is what it called sequence. Elements are required to distinct in term sequence. Same, thus, yep, thus is valid sequence of length 3, but ABA is a set with 2 elements, not 3. Yeah, so you see, sequences, wait. The elements of a set are required to be distinct, but terms in a sequence can be the same. Thus, ABA sequence is a valid sequence of length 3. You see, this is length 3. Sequence can be identical. The A is identical to the A, but in a set, it cannot be identical. But in a set, ABA is a set with 2 elements, not 3. 2 elements, only A and B. Because A is identical to A and it cannot be 3 in terms of a sequence have a specified order, but the terms in a sequence have a specified order, but the elements of a set do not. So ABC, this is the order. This is 1, 2, 3. A and ACB are different sequences. But ABC and ACB are the same set. Okay. Text differ or notion for the empty sequence we use for the empty sequence and 5 for the empty set. So empty set, okay. That's all what I need for now. Okay. Every non-empty set of non-negative integers has a smallest element. This statement is known as the will ordering principle. Wait, order does matter in sequences, but it doesn't matter in a set. Do you believe it? Seems sort of obvious, right? But notice how tight it is. It requires a non-empty set. It is false for the empty set which has no smallest element because it has no elements at all. And it requires a set of non-negative integers It is false for the set of negative integers and also false for some sets of non-negative rationals. For example, the set of positive rationals. Okay. So the will ordering principle captures something special about the non-negative integers. Will ordering proofs. While the will ordering principle may seem obvious, it is hard to see offhand why it is useful. But, in fact, it provides one of the most important proof rules in discrete mathematics. May seem obvious, it's hard to see offhand why it's useful. But in fact, it provides one of the most important proof rules in discrete mathematics. In fact, looking back, we took the will ordering principle for granted in proving that square root of 2 is irrational. That proof assumed that for any positive integers m and n, the fraction m over n can be written in lowest terms, that is, in the form of mn dash where m and n are positive integers with no common factors. How do we know this is always possible? Okay, so now we're going into some details of proofs. Suppose the contrary, that there where m and n belongs to z positive, such that the fraction n over n cannot be written in lowest terms. Now let's see be the set of positive integers that are numerators of such fractions. Then m belongs to c, so c is non-empty. Therefore, numerators, are they bast or maqam? Because denominators, I think denominators are maqam, but let's check. Numerators. I don't need AI ones. Is the top? Yes, it is bust. Denominator is okay. So that are numerators of such fractions, then m, which is the numerator, fraction n, belongs to c, so c is non-empty. Therefore, by will ordering, there must be a smallest integer. Okay, because the will ordering says that there has to be a small, the sets of here we just said it. The sets are, there got to be a smallest integer in a set. Okay, of Natural numbers, non-empty natural numbers set. M0, which is the smallest, belongs to C. Okay, so by definition of C, there is an integer n, the smallest, larger than 0, such that the fraction m0 over n0 cannot be written in lowest terms. What do you mean? This means that m0 and n0 must have a common factor. P is larger than 1, but m0 over p and n0 over p equal m0 over n0. If they have a common factor, of course. If they have a common factor. So any way of expressing the left-hand fraction in lowest terms would also work for m0 over n0, which implies the fraction m0 over p over n0 over p cannot be written in lowest terms either. So any way of expressing the left-hand fraction in lowest terms would also work for m0 over n0, which implies the fraction m0 over p and n0 over p cannot be written in lowest terms either. What does this mean? Did you get it? There must be a smallest integer m0 belongs to C. So by definition of C, there is an integer n0 larger than 0, okay, such that the fraction, the smallest over the smallest, cannot be written in lowest terms. It cannot be written in lowest terms. Why? This means that m0 and n0 must have a common factor. If they have a common factor, let's check them out. 4 over 2. Okay, that could be 2 over 1. So what do you mean? This means fraction cannot be written in lowest terms. What do you mean? Equal m0 over n. It's equal m0 over n. It's the same. Because 4 over 2 is 4. Well, it's 2. So it's the same as, okay, but because the denominator is the common factor. See something different? 16 over 2. 16 over 2. Okay. Anyway, if expressing the left-hand fraction in lowest terms would also work for m0 over n0, which implies the fraction m0 over p n0 cannot be written in lowest terms either. What does this mean? So by definition of C, the numerator m0 over p is in C, but m0 over p is less than m0, so by definition, okay, m0 p is in C, but m0 over p is less than m0, which contradicts the fact that m0 is the smallest element of C. Of course, is the smallest element of C. So 16 over 2 over 4. Let's say 16. So over 4 over 4. 16 over 4, it can be 16 over 4 here and 16, wait, 16 over 8, 16 over 8, 16 over 8. If it's 16, or we can divide the 16 by 2 and divide the 8 of 2, the p can be 2, so the 16 is going to be 8 over 4. So it's not the smallest, still not the smallest terms. So yep, if they have a common, which means if they have a common factor, they are not in their lowest terms. I think common factor, which is 2 by the way here, so 16 over 8, we can divide the 16 by 2 and the 8 by 2. That's no, well, and still the 4 and the 8 can be divided by 2 again. Well, we'll have to take the largest common factor, which is it is 8, because 16 over 8 is 2, right? Okay. So, but okay, which contradicts the fact that M0 is the smallest element to C. Since the assumption that C is non-empty leads to a contradiction, it follows that C must be empty. The assumption that C is non-empty leads to a contradiction. It follows that C must be empty. That is, that there are no numerators of fractions that can't be written in lowest terms. That there are no numerators of fractions that can't be written in lowest terms, and hence there are no such fractions at all. We've been using the well-ordering principle on the sly from early on. There are no fractions that cannot be written in the lowest terms, because it's going to be okay. Wait. Hence, there are no such fractions at all. What do you mean? Of fractions that cannot be written in lowest terms. Okay. Then hence, there are no such fractions at all. Yep, they all can be written in their smallest terms. We've been using the well-ordering principle only on the sly from early on. Oh my god. Discrete math is different than any other math. Template for well-ordering proofs. Perhaps English is also a barrier in this case. Template for well-ordering proofs, more generally, to prove that Pn is true for all n belongs to n. Template for well-ordering, more generally, to prove that Pn is true for all n belongs to n natural numbers. Why this two commas? What does it mean? Using the well-ordering principle, you can take the following steps. Okay, this is the steps. Define the set C of counterexamples of counterexamples to be being true. What does that mean? Namely, define, we got a reference here, C by, what did they call this? By equal, by definition is equal to the set, okay, equal to n, the set n belongs to n natural numbers, and p such that Pn is false. What does that, or does this imply such, I don't know, Pn is false. Okay, so this is the counterexample. The counterexamples to P being true. Okay, so this is what the counterexample means. Just Pn is false. So use a proof by contradiction and assume that C is non-empty. Use a proof by contradiction and assume that C is non-empty. By the will ordering principle, there will be a smallest element n in C. By the way, in chapter 2, at the end of it, there is a set of rules. We'll come back to it. We'll get to it in solving some problem sets. How to write a clean proof. It's like how to write a clean code. There are a set of rules. We'll get to it. I should have read it before doing problem sets 1. It would have been very helpful. It clarifies the way you write proof. By the will ordering principle, there will be a smallest element n in C. Assume that C is not. Use a proof by contradiction. Proof by contradiction we've been through at chapter 2. And assume that C is not empty. Okay. Reach a contradiction somehow, often by showing how to use n to find another number of C. Reach a contradiction. You want to reach a contradiction, and it's often done by showing how to use n to find another member of C that is smaller than n. This is the open-ended part of the proof task. Conclude that C must be empty, that is, no counterexamples exist. QED. Is no counterexamples exist. QED. Okay, this means that you are about to see an informal proof by contradiction. As we learned in section 2.6.2, the notion means the set of all elements n for which for which P, they are for none. Okay, which Pn is false. Okay. Examples. Let's see examples. Let's use this template to prove. Theorem. 1 plus 2 plus 3 plus etc. plus n equal n multiplied in n plus 1 over 2. Okay. Okay. It is over 2. Why is it over 2? I get it's multiplied. It's multiplication. It could have been just n plus 1 because 1, 2, 3. But no. It has to become more complicated. Okay, for all non-negative integers. And first, we better address of a couple of ambiguous special cases before they trip us up. If n equal 1, then there is only one term in the summation. And so 1 plus 2 plus 3 plus is just the term 1. Don't be misled by the appearance of 2 and 3 and the suggestion that 1 and n are distinct terms. Then there is only one term in the summation, and so 1 is just the term 1. Should you try the suggestion that 1 and n are distinct terms? Try it. 1 plus 1, that's 2, and 1, that's 2 over 2, that's 1. Okay, it is 1. Okay, don't be misled by the appearance of 2 and 3 and the suggestion that 1 and n are distinct terms. Okay, I don't know what that means, but if n is less or equal 0, then there are no terms at all in the summation. By convention, the sum in this case is 0. Yes, of course it's going to be 0 because 0 over 2, wait, the summation is 0, wait, minus 1, well it's going to be 0. Okay, minus 2 minus 2 multiplied, well this is going to be minus 2 and plus 1 and minus 1, so it's going to be 2 over 2. Okay, minus 3, wait, minus 3 and plus 1, that's a minus 2. Minus 2 multiplied by minus 3, that's a 6 over 2. It's going to be 3. So what are we talking about? Why? If n is less or equal 0, then there are no terms at all in the summation. By convention, the sum in this case is 0. You know why we don't use I think I just came up with this. We don't use negative numbers because they're always going to be a smaller, and for an infinity. This is going to be minus infinity. It's always going to be a smaller because minus 1 is larger than minus 2. So there's always going to be to infinity a lowest term. Am I correct? No? I don't know. By convention, the sum in this case is 0. So while the dots notation is convenient, you have to watch out for these special cases where the notion is misleading. In fact, whenever you see the dots, you should be on the lookout to be sure you understand the pattern, watching out for the beginning and the end. These dots. You should be on the lookout to be sure you understand the pattern. Watching out for the beginning and end. We could have eliminated the need for guessing by rewriting the left side of 3.1 with the summation notion. Okay, sigma, which is all, everything, I equal well, it's n or sigma I 1 is less or equal I less or equal n. So I is gonna be less than n, but I is larger than 1. Okay, larger or equal 1. And I could be less or equal n. Both of these expressions denote the sum of all values taken by the expression to the right of the sigma, as the variable. I ranges from 1 to n. I ranges from 1 to n. I ranges from 1 to n. The right of the sigma as the variable. The expression to the right of the sigma as the variable. I ranges from 1 to n. Okay, from 1 to n. Both expressions make it clear what they means when n equal to 1. From 1 to n. Both expressions n equal to 1. The second expression makes it clear that when n equal 0, there are no terms in the sum. There are no terms in the sum. Though you still have to know the convention that a sum of no numbers equals 0. If no numbers equals 0. The product, the sum of no numbers equals 0. The product of no numbers is 1. The product, which means the multiplication. The product of no numbers is 1. By the way, this explains this. You could write it. This explains this. If n is 1, there is only one term in the summation. And so on is just the term 1. Do not be misled by the appearance of 2 and 3 and the suggestion that 1 and n are distinct terms. Let's check this out again. So n, suppose n is 2. It's gonna be 1 plus n. They're gonna be 1 plus n plus 2. So am I correct? Wait, let's take this. 2 multiplied by 3, that's 6. Over 2, that's 3. What does that mean? What do you mean? Wait, n plus 1, 2 plus 1, that's 3. And 2 multiplied in 3, that's 6. Over 2, is 3. And 3 is equal 1 plus 2. Am I correct? Okay. Do you get it now? Did you get it? Did you get this? What is this is implying for? So 3, it's going to be 1 plus 2 plus 3 if we plug it here. Check this out. 3 plus 1, that's 4. Multiplied in 3, that's 12. Over 2, that's 6. Okay? 6 is equal to 3 plus 2 plus 1. Plus 1. So that's which Correct. It's 3 plus 2, that's 5, plus 1, which is 6. So it is 6. This is what it's like. So here it says, if n equal 1, there is only one term. There is only one term. 1, it's going to be 1. There is no 1 plus 2 plus 3. It's going to be 1 equal 1 multiplied by 2, that's 2 over 2 equal 1, which is 1. That's it. Okay. So this is what this says. And if n is less than, then there are no terms. There are no terms. Because it's going to be false. Let's check this out. If less or equal 0, let's check it. 0. There are no terms. That's it. 0. It starts with 1. There are no. But let's check. 0 over 0 over, it's 0. Okay. It's equal 0. We could have added 0 here. Why not, man? 0 plus 1 plus 2. It doesn't affect. The 0 doesn't affect. Okay. Let's check something else. Minus 1. Minus 1. Minus 1. Minus 1. Minus 1 plus 1. That's 0. Over 0 over 2. That's 0. So it cannot be minus 1 plus. Well, minus 1 plus 0 plus 1. That's 0. I think it works. I think it works even on negative numbers. Okay. So minus 3. Wait. Minus 3. Let's check. Minus 3. Well. Yeah, but the n is gonna be on the other side. It doesn't work. The n is 3. This n suggests the largest term. The largest term, which is this is the smallest term, so it doesn't work. It doesn't work. It doesn't work. The n suggests the largest term is gonna be. It's okay. So suppose the n, because wait. Yeah, it doesn't work. It doesn't work on minus and 0. Wait, 0. It's gonna. There is no. It's 0. But I think it works on 0 though. 0 is the smallest. What are we talking about? Okay, whatever. If n is less or equal 0, then there are no terms at all in the summation. There are no terms. By convention, the sum in this case is 0. 0, okay. So while the notion is convenient, so while the dot notions is convenient, which is this dot notion, you have to watch out for these special cases where the notion is misleading. In fact, whenever you see the dots, you should be on the lookout to be sure you understand the pattern, watching out for the beginning and end. We could have eliminated the need for guessing by rewriting the left side of 3.1 with summation notation. With summation notation. The need for guessing by rewriting the left side of 3 points. Okay, with summation notation. So this basically means this. Means this two dot notations. This is what it means. Starts with 1 to n, and it goes to n. Okay, so both of these expressions denote the sum of all values taken by the expression to the right. We could have element for guessing by writing the left side of 3.1. Wait, this is 3.1. Yeah, sigma, which means sigma I, this is I, and yeah, n is the largest, I1 is the smallest, so I could be 1, it could be, this is what it means, it could be 1, 2, 3 to the n. Okay, and you can write it by this 1, I, and n. Okay, I, and it could be I. Okay, both of these expressions, the summations of I, both of these expressions denote the sum of all values taken by the expression to the right of the sigma as the variable. I ranges from 1 to n. Okay, both expressions make it clear what 3.1 means when n equal 1. The second expression makes it clear that when n equal to 0, there are no terms in the sum, though you still have to know the conventions that a sum of no numbers equal 0. The product, okay, the product of no numbers is 1. The product of no numbers is 1. By the way, product of no numbers is 1. What does that mean? Oh, okay. It's 1. Which is 1? No numbers equal 0. The product of no numbers is 1. By the way. Okay, back to the proof. I've seen the product before. Now I'm confused. I've seen the product before. I think I read it and then again I read it. Okay. Product of no numbers is 1, by the way. The product. Product. I think it's multiplication. Means in math. That is the answer you get when you multiply two or more numbers. Yeah, so I was right, it's multiplication. Okay. So if no numbers are multiplied, the product of no numbers at all. It's 1. I don't know how that makes sense. Order does not matter. Changing the order. Multiplying by 0 any as a product of 0. Multiplying by 1 any number keeps its own value. This is identity property. Times decimals and fractions. Okay, algebra. Okay. Beyond numbers, advanced math uses product for other objects like Cartesian products of sets or direct products of groups. If you'd like, advanced math for other objects like Cartesian products of sets or direct products of groups. If you'd like, let me know the kind of fraction. A product of no the product of no numbers. If no numbers. Then math, the product of no numbers is equal to 1. This concept is called the empty product. This is called, the math Product of no number is equal to 1. This concept is called the empty product or nullary product. It acts as the starting baseline for multiplication, just as adding no numbers. An empty sum equals 0. Why it equals 1? Most users on Reddit agree that 1 is the multiplicative identity, meaning multiplying by any number by 1 leaves it unchanged. When you start a chain of multiplication, you implicitly start with 1 before multiplying by the next factor. If there are no factors, you are left with just the starting value, which means it's going to be 1, setting 1 multiplied by 1, which is 1. Setting it 1 keeps math rules consistent and prevents equations from breaking. Common examples: 0 factorial, defined as 1 because it represents multiplying 0 numbers together. Okay. 0 with power, that's 1. Any number to the power of 0 equals to 1 for this exact reason. The factorial of 0 represents multiplying 0 numbers together. 0 numbers together. Okay, would you like to explore how the empty sum? Well, this is even the factorial because it's going to be 0 multiplied by or added by, I forgot the factorial. Is it multiplication or plus sign, or is it adding? But it's going to be 0, which is 0. If we multiply it by 0, it's going to be 0. It's going to be 0. Okay. I don't get it. It represents multiplying 0 numbers together. You're not multiplying. Here, wait. 1 multiplied 0 times is going to be 0. This, you take it, doesn't have to make sense. You take it as a granted. There is no multiplication. F0, there is no multiplying. Okay. Both of these denote this. Okay, where were it? Proof by contradiction. The product of 0 numbers is 1. Of 0 numbers. Of no numbers. Okay, we have to know that the convention that the sum of no numbers equals 0. Sum of no numbers equals 0. The product of no numbers is 1. The sum of no numbers equals 0. No numbers are added. The product of no numbers is 1. Wait. 0 factorial defined as 1 because it represents multiple. So the factorial is multiplication. Factorial is multiplication. If we take 5 factorial, it's gonna be 1 multiplied by 2 multiplied by, am I correct? Right. 5 factorial. 120. Yep. It's multiplication. Yep. It's product. Okay. The product of no numbers is 1, by the way. Okay. Okay, back to the proof. Proof by contradiction and use of the will ordering principle. Assume that the theorem is false. Assume that the theorem is false, then some non-negative integers serve as counterexample to it. Let's collect them in a set. So C by definition is n equal to n equal to the natural numbers 1 plus 2 plus 3. Okay, so this is sigma, what we talked about, not equal n over 2. Okay, so this is what this is by contradiction. This contradiction, assume that the theorem is false, not equal. Okay, so this is by contradiction. Some non-negative integer serves as counterexample to it. Let's collect them in a set. Okay. By our assumption that the theorem admits counterexamples, C is a non-empty set. The theorem admits counterexample. C is a non-empty set of non-negative integers. So by doing the will ordering principle, C has a minimum element. Call it C. Did we say non-negative? Then some non-negative integers serve as a counterexamples to it. Let's collect them. Okay. Assumption that the theorem admits counterexamples. C is a non-empty set of non-negative integers. So by the will ordering principle, C has a minimum element. Call it C. That is, C is the smallest counterexample to the theorem. Since C is the smallest counterexample, we know that 3.1 is false for n equal C, but true for all non-negative integers. N less than C, but for n less than C. Wait. But true for all non-negative integers, n is less. What does that mean? But 3.1. I don't get this. Since C is the smallest counterexample, that's 1. We know that 3.1 is false for n equals C, because there's gonna be no multiplication. So it's only 1. No adding. But true for all non-negative integers. N is less than C. But C is the smallest. What are you talking about? But 3.1 is true for n equals 0. So C larger than 0. So C larger than 0 equals 0. So C is larger than. This means C minus 1 is a non-negative integer. And since it is less than C, equation 3.1 is true for C minus 1. That is 1 plus C minus 1. Okay, wait. This is different. C minus 1 is a non-negative integer. C minus 1. Yep. That's going to be 0. Is a non-negative integer. Thus, this means, any but true for integers n less than Z. But 3.1 is true for n equals 0. So C larger than 0. This means C minus 1 is a non-negative integer, and since it is less than C, equation 3.1 is true for C minus 1. That is 1. Plus equal C minus 1 equal C minus 1 in C over 2. We changed the theory we gave it a counterexample. This is the theorem admits counterexamples. C, it's a C now. It's not N anymore. C is a non-empty set. Is a non-empty set. Is still non-empty set of non-negative integers. So by the will ordering principle, C has a minimum element. Okay, that's one. Call it C. Okay, is the smallest counterexample. We see smallest counter. We know that 3.1 is false for n equals c, small, but true for all non-negative integers n. Okay, how do we know that? It is true, but how do we know? Because 1 minus 1, okay, it's gonna be 1, it's gonna be 0 over 2. Okay. But true for everything else? How? Okay, let's take 2 for example. 2 minus 1, that's 1. 1 and 2 over 2, that's 1. It doesn't. That's 1, which is 1 plus 2 is not. Okay, is 4. But 3.1 is true for n equals 0. What does it say? 3.1 is false for n equals c. What are we talking about? For n equals c. But true for all non-negative integers, n is less than c. Small. C small. How can it? I don't understand. But 3.1 is true for n equals 0. So c larger than 0. This means c minus 1 is a non-negative integer. That's correct, it's non-negative. It's gonna be, okay. And since it is less than c, equation 3.1 is true for c minus 1. That is, it's gonna be c minus 1. So let's take 3 for example. But then adding c to both sides, we get I don't get how this is true. C minus 1, which means what happened? 2 is equal to minus 1. I don't get it. I do not get it. But anyways, but then adding c to both sides, we get plus c equal, okay, equal c and c plus 1 over 2, which means that 3.1 does hold for c. After all, this is a contradiction and we are done. Means that 3.1 does hold for c. After all, this is a contradiction and we are done. I don't get it. I do not get it. I know how he. What does he mean? We plugged instead of the n. We plugged c minus 1. Wait. I don't get it. I don't get it. Let's go from the start. What does it say? N over 2. Okay. Plus 1 over 2. Okay. 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 So what we did is proof by contradiction and use of the well ordering principle. The well ordering principle again is, what does it mean? This statement is known: every non-empty set of non-negative integers has the smallest element. Has the smallest element. Okay, this is what does it mean. The set is non-empty and it consists of non-negative integers and it has the smallest element. Okay, so this is the well ordering proof. Everything else is not changed. The contradiction. Template for well ordering proof. Use a proof. Define the set C of counter examples to P being true to counter examples of C. Namely, define A by definition n belongs to natural numbers. Pn is false. Pn is false. What did we do? Define the set C. Let's use these templates to prove. For all non-negative integers n. First, we better address of a couple of ambiguous special cases before they trip us up. If n equal to 1, then there is only, okay, we get this, we've done this, we've done this. This is the special cases. Okay. Both these expressions denote the sum of all values taken by the expression to the okay, that sum equals product. Okay. Back to the proof. B. Proof by contradiction and use of well ordering principle. Assume that the theorem is false. Then some non-negative integers serve as counterexample to it. Get some non-negative integers also from this set as counterexamples to it. Let's collect them in a set. C by definition n belongs to n, 1 plus 2 plus 3 plus n. This n does not equal this. Okay, this is the counterexample. This counterexample. Okay. Then what we did, by our assumption that the theorem admits counterexamples, C is a non-empty set. Again, now we are in C. C is a non-empty set. Where are we in the proof? The template. There will be a smallest element in C. Reach a contradiction. Okay, I don't care about reach. In C. Okay. Now, by assumption that the theorem admits count, example C is a non-empty set of non-negative integers. So by the well ordering principle, C has a minimum element. Call it C small. That is C small. C is the smallest counterexample of the theorem. Okay, since C is the smallest counterexample, we know that 3.1, again, that is false for n equals C. for n equals c. Okay. But true for all non-negative integers n less than c. Okay. But 3.1 is true for n equals 0. I don't know what does this mean. For n equals 0. Why? I don't know. So c is larger than 0. Okay, because we know. Okay, this means c minus 1 is a non-negative integer. Non-negative integer. That's true because c is larger than 1, is larger than 0. And c minus 1 is a non-negative integer. Okay, because it's larger than 0 anyways. So if c is 2, it's going to be 1. Okay, non-negative. And since it is less than c, equation 3.1 is true for c minus 1. That is. Okay. So 1 plus 2 plus 3 plus c minus, okay, that's c minus 1, equal c minus 1, which is the n over nc over 2. Wait. It's the same over there, but what does it say here? This is the C is the smallest counterexample. It is the smallest counterexample. We're giving it a counterexample. We don't care. But what it says, we know that 3.1 is false for n equals c. N equals c. If n equals c, because n is true. 3.1, this one, because it's a counterexample. This one is false. Negative serve as a counterexample to it. Assume that the theorem is false, then some non-negative integer, some. Suppose there is only one non-negative integer, serve as a counterexample to it. Let's collect them in a set. Okay. Does not equal n because we already assumed that. Okay, which means that when n equals c, which we suppose that okay, wait. So by the way, c has a minimum element. Call it c. C minus c is the smallest counterexamples to the theorem. So which is some non-negative integer. Okay. Since c is the smallest counterexample, we know that 3.1 is false for n equals c. It is false. That's correct. It is false for n equals c because n over c is actually equal. N is equal n. So when it doesn't equal, this becomes c. Okay. So okay. I don't care how you get it, but I get it. N equals c is false. When n equals c is false, c is small. But true for all non-negative integers, n less than c. It is true for everything less than c. But 3.1 is true for n equals 0. 3.3 or 3.1, which is true for n equals 0. So n is true for n equals 0. This is part of the counterexample. I don't know. Okay. So this I don't get it. But c is true for n equals 0. We said C is a special case, but okay. So C larger than 0. We get that C is larger than 0. This means that C minus 1 is a non-negative integer. And since it is less than C, okay, since it is less than C small, this C minus 1 is less than C small. Equation 3.1 is true for C minus 1. That is. So now we plug in the C minus 1 instead of the C. Okay, C minus 1, wait, is true for C minus. Then equation 3.1 is true for C minus 1. That is, instead of the n, we can write the n as C minus 1. So again, what did we say? C n plus 1. So we plugged the C minus 1 here. C minus 1. Okay. So let me be precise. I don't like to unplug my mouse, but C minus 1 over C minus 1 plus 1 over 2 is gonna be equal to C minus 1 multiplied in, this goes with this, NC multiplied in C over 2, which is the same. Okay, so you see what we did, we plugged in the C minus 1 instead of the n, so it became this C minus 1. But then adding C to both sides, then we add C to both sides. We added C plus C here plus C here. Okay. What happened? This is the n. Okay? Remember that this is the n. Now we're adding plus C small, which is what we assumed, that there is a counterexample. There is some kind of fucking non-integer number where the n equation doesn't equal that 3.1 equation. Okay, so C small, we added the C small, equal C plus C. Now we're adding C. We multiplied the C here. C, this is C square minus 1, and then we added the C, so it became C square. Wait, add the C. Wait. C. Yep, it's minus C, so it became C square minus C plus C. Plus 2C? Why plus 2C? Wait. Because it's over 2. Okay. So C square minus C is from here, and plus 2C. What happened is we multiplied here by 2, multiplied the C. This should be C plus C. I don't get how we get plus 2C here. Plus C. This is what I get. I get C square minus c plus, wait, over 2 plus c. What I have is that this is plus 1. This is c over 1. So what am I gonna do in the plus 1? In this, I'm gonna flip this side, let's say. What happened here? Okay. So this over this over this. So what's gonna happen is equal c square minus c. This over this is 2c plus 2c. Correct. 1 over 2 is 2. Correct. Then I take the common factor, which is the c. Common factor is c over. And here c, if we multiply c by c, then this is c minus this minus 1. Minus 1. 2c. See the common factor. Plus 1. Yeah, plus 1. C plus 1. How do we do this? Common factor. C over c. C square. Okay, wait. This c minus c and plus 2c are c. So before this step, what happened is that this becomes c square and minus c plus 2c is plus 1c. So over 2. Yep. Yeah, now it makes sense. So we take the c as a common factor and it becomes c plus 1 over 2. Over 2. Okay, now which means that 3.1 does hold for c. After all, this is a contradiction, and we are done. I think. Did you get this? I got it. I mean, here is another result that can be proved. Sorry, guys, I'm gonna have to go. Take some time off. Sorry. Perfection. Bismillah. Oh, God damn it. Oh, my God. Oh, my God. Oh, my God. Oh, my God. So, which page are we in? See, it takes time. This course takes time. Oh, my God. Oh, my God. Oh, God damn it. Induction. There is a chapter, another chapter that's strong induction. Are we gonna take all this today? I don't think so. No, wait. Let's do this. Let's go for the course readings chapter. No, number theory. So induction, it's both. Yep, it's both lecture 1 and lecture 2. Induction and strong induction all in this. So it takes 2 weeks. So it's both in chapter 3. 2 lectures. I haven't watched lecture 2 yet, but I'm doing it. This is the weird thing about it. There is no, it's not like Khan Academy or you have to divide your time yourself. So where are we at? So does hold for C. Does hold for C. After all, this is a contradiction and we are done. Okay, here's another result. Excuse me, guys. I'm gonna have to go somewhere. Okay, here's another. Here is a. Here's another result that can be proved using will ordering. It will be useful in chapter 4 when we study number theory and cryptography. Okay, we're gonna study cryptography. That's mad. Theorem. Every natural number can be factored as a product of primes. Primes, we've previously saw their definition in chapter 1. I think they are, they can be, what? They can be divided only by one and themselves. I think. Am I correct? Theorem. Every natural number can be factored as a product of primes. As a product of primes. Okay. Primes. Prime. God damn it. Prime. Prime number is a whole number greater than 1 that can only be divided evenly by 1 itself and itself. By 1 and itself. 5 can only be divided by 1 and 5, making it a prime number. Okay, so I was correct. Okay, going back. Okay, as a product of primes. Okay, can be factored as a product of primes. Proof by contradiction and will ordering. Assume that the theorem is false. Assume that the theorem is false, and let C be the set of all integers greater than 1 that cannot be factored as a product. Let C be the set of all integers greater than 1 that cannot be factored as a product. The product. Why? Why is it greater than 1? I don't know. That cannot be, because 1 cannot be factored. Can it? I don't know. It's small as a product of primes. Okay. We assume that C is not empty, and derive a contradiction. We assume that C is not empty and derive a contradiction. We assume that C is not empty. We assume that C is not empty. That C is not empty. Okay, not empty. And derive a contradiction. Okay. First, the theorem is false, and contradiction because it's by contradiction. So if C is not empty, there is at least element N belongs to C. N belongs to C by will ordering. The N cannot be prime. By the will ordering, the N cannot be prime. By will ordering, the N can't be prime. Because a prime by itself is considered a length 1 product of primes. And no such products are in C. Because a prime by itself is considered a length 1. Because a prime by itself is considered a length n, a length 1 is considered a length 1 product of primes, and no such products are in C. Because a prime by itself is considered a length 1 product of primes, and no such products are in C. What do you mean? N and C. Okay. What did we say? A set of all integers greater than 1 that cannot be factored as a product of primes. Okay. So at least one element in N belongs to Z by will ordering. Okay. Because it's false, and by contradiction. Because it's false, there must be an N which belongs to the natural numbers that cannot be factored by a product prime. Then N cannot be prime. N can't be prime because a prime by itself is considered a length 1 product of primes, and no such products are in C. Because primes are in natural, because natural numbers consist of primes also, so it cannot be prime. Because a prime itself is considered a length 1 product of primes, and no such products are in C. Okay. In C, which is the one that cannot be factored as a product, all integers greater than 1, which is great, that cannot be products of prime. So C by will ordering is all non-negative integers, which is, and they're greater than 1 that cannot be factored as a product of primes. Okay, we assume that, I think, because 1 is a prime. So am I correct? Let's check primes. Okay, starts with in 2. Starts in 2. It's 3 prime 2, 3, 5, 7. Except for the number 2, all primes numbers are odd. Okay. Building blocks. Every whole number greater than 1 is either a prime itself or can be made by multiplying prime numbers together. The fundamental theorem of arithmetic. Prime itself or can be made by multiplying prime numbers together. So what we're trying here to say? It says every natural number can be factored as a product of prime. By contradiction and well ordering, assume that theorem is false and let C be a set of all integers greater than all non-negative. Well ordering, we said well ordering, every non-empty set of non-negative integers has the smallest element. Okay. And why it's useful, but in fact, okay. proof by contradiction and well ordering. Assume that the theorem is false, and let C be the set of all integers greater than 1 that cannot be factored as a product. That cannot be factored as a product of primes. Assume that the theorem is false. Theorem is false. Okay, and let C be the set of all integers greater than 1 that cannot be factored as a product of primes. Assume that the theorem is false, and let C be a set of all integers greater than 1 that cannot be factored as a product of primes. We assume that C is not empty and derive a contradiction. If C is not empty, there is at least element n belongs to C by well ordering. The n can't be prime because a prime is a product of prime, so which will hold in that case. So n must be a product of two integers, a and b, where a and b are larger than 1 and less than n. Since a and b are smaller than the smallest element in C. Smaller? Why? Why are they smaller than the smallest element in C? They are always smaller, huh? Since A, B are smaller than the smallest element in C. We know that AB does not belong to C. In other words, A can be written as a product of primes, P and P as a product of primes. Therefore, N equal P can be written as a product of primes, contradicting the claim. This is N can't be prime. That's understandable. So N must be a product of two integers. Okay, where A and B is larger than 1 and n and less than n. Since and less than n the largest, because they are the small. It is the smallest. It has to be the smallest. It has to be the smallest according to well ordering. It has to be the smallest. Since A and B are smaller than the smallest element in C. This I don't get it. C is larger than 1, so it's larger. And A and B are smaller than, since I don't get it. Let's use AI. Let's use AI. Seriously. Why am I keep going back and forth? Why? This is the classic well-ordering proof that every integer larger than 1 factors into primes, sometimes called the fundamental theorem. Existence part uniqueness is a separate theorem. Let me break down why each step, since the whole proof hinges on one clever move. The setup, proof by contradiction. Instead of directly proving every n has a prime factorization, they assume the opposite. Suppose some numbers don't call that bad set C. If C is non-empty, well ordering says it has at least element n, at least element, at least, which means C must at least, wait. Will ordering say it has at least, it has a least element, a least element, n. Okay. The goal is to show n leads to a contradiction, which means C must actually be empty. Why n can't be prime? C must actually be empty. What are you talking about? They assume the opposite. Suppose numbers, call that bad set C. Okay. If C is non-empty, will ordering say it has a least element n. The goal is to show n leads to a contradiction, which means C must actually be empty. Why n can't be prime? If n itself were prime, then n is already a product of primes. Okay? Products with just one factor. This counts by convention. So n wouldn't belong to C in the first place. Since n belongs to C, n must be composite. N wouldn't belong to C in the first place. Since n belongs to C, n must be composite. Why n equal AB with A, B strictly between 1 and n? Composite just means n has some factorization. N equal A, B, where neither factor is 1 or n itself. That's the definition of composite, nothing fancier. The key move AB doesn't belong to C. This is the step that makes the whole proof click. N is the smallest element of C. That's what well ordering bought us. Since A is larger than 1, less than n, and B is larger than 1 and less than n, both A and B are smaller than n. But n is the smallest bad number. So anything smaller than n is not bad. Hence, A belongs to C and B, hence A doesn't belong to C and B. That means A and B each do have prime factorizations, closing contradiction, multiplying them together and equal AB. That's a product of primes, but n was supposed to be nc. The set of numbers without a prime factor contradiction, so C can't have a least element, and by well ordering C must be empty. This is smallest counterexample of technique you will see constantly in assume a bad set is non-empty. Okay, grab its minimum via well ordering. Then show that minimum can be broken into smaller pieces that are themselves fine, not in the bad set, which forces the bad thing to actually be fine too. It's essentially strong induction in disguise. In fact, this same proof could be written as a strong induction on n with no real change on logic. One thing to flag, given the gap you've hit before in PS1, The proof doesn't just assert A and B have factorizations, it explicitly names them and then explicitly multiplies them to reconstruct n's factorization. That explicit reconstruction step is what closes the loop back to the original claim, worth limiting that move, worth limiting, worth imitating that move in your own proofs when a strong induction hypothesis is doing the work. Zero. Humer's false. And let C be the set of integers greater than 1 that cannot be factored as a product of primes. We assume that C is not empty and derive a contradiction. If C is not empty, there is a least element. N to C. What does this mean? C doesn't belong. Can't write. N belongs to C. Okay. By will ordering. The N can't be prime because primes okay. So N must be a product of two integers, A and B. It must be a product of two integers where A and B are less than N and larger than 1. Every natural number can be factored as a product of primes. Can be factored as a product of primes. So must be a product of two integers A and B where A and B less than N, since A and B are smaller than the smallest element in C, which we know that A and B don't belong to C. In other words, A can be written as primes and B as a product of primes. So, what does this say? Well ordering, assume that the theorem is false and let C be the set of all integers greater than 1. That cannot be fact. Let C be the set of all integers greater than 1. That cannot be factored as a product of primes. Okay. We assume that C is not empty. C is not empty, and derive a contradiction. If C is not empty, there is at least element N belongs to C by will ordering. If C is not empty, C, which is larger than 1, that cannot be factored as a product of primes. We assume that C is not empty. C is not empty. And derive a consequence. if C is not empty, C, which is the larger than 1, and that cannot be factored as a product of primes. Okay, there is at least, so n, if C is not empty, there is at least element, there is a least element via non-empty, because by will ordering. N belongs n belongs to Z, which is the least. N is the least by will ordering. The n can't be prime because primes itself is considered a length 1 product of primes, and no such products are in C. So n must be a product of two integers a and b, where again a and b are the largers, uh, the C, and b is less than n, where they are larger than 1, and less than n. What the fuck is n doing here? We assume that the theorem is false, and let C be the set of all integers greater than 1 that cannot be factored. We assume C is not empty, so there is a least. So C is not empty, there is a least element. N belongs to C. By will ordering, n can't be prime, because a prime by itself is considered an n. So n must be a product of two integers. N must be a product of two integers, a and b, where they are larger than 1 but less than n. Since a and b are smaller than the smallest element in C, we know that a and b do not belong to C. In other words, A can be written as a product of primes and B as a product of primes. Therefore, N equal P Q1 Q can be written as a product of primes. Because they are primes. I don't think they are primes. What does a product of primes mean? Wait. What does a product of primes mean? They all primes. Is exactly a product of primes, just means you multiply together some primes. Repeated 12. All primes. So they are primes. Wait, so this means they are primes. Okay, it clicked. A and B are primes, since they are less than n, because n is gonna be what? The least. So n, so n, which belongs to C, which is this set of numbers that cannot be a product of primes. And by will ordering, n is the least of them, which is the smaller number of these, not primes, which is the smaller number of this set that cannot be a product of primes, okay? So n, okay? By definition, a product of means that these numbers that the n is going to be a product of are going to be less than the least number of C, which are the set of numbers that cannot be a product of primes. Okay? They cannot be a product of primes. But these numbers are a product of primes, A and B. They can be a product of primes. So there is, wait, they are a product of primes. So what does this leave n with? Since A and B are smaller than the smallest element in C, we know that they don't belong. In other words, A can be written as a product of primes and B as a product of primes. Therefore, n as a product is multiplied in A and Q, and which meaning that those primes that A and B are a product of can be multiplied together to give n, which is primes, which are primes. Therefore, can be written as a product of primes, contradicting the claim that n belongs to C. Our assumption that C is not empty must be therefore be false. Do you get it? Ordinary induction. Do you get that? Okay. Induction is by far the most powerful and commonly used proof technique. Induction is by far the most powerful and commonly used proof technique. Okay. In discrete mathematics and computer science, in fact, the use of induction is a defining characteristic of discrete as opposed to continuous mathematics. Okay. So, what does this mean? What is the difference? Discrete mathematics studies countable, distinct, and separate objects, like integers, graphs, and logical statements, whereas continuous mathematics deals with smooth, unbroken changes and real numbers, like calculus curves and manifolds. Think of discrete math as individual steps on a staircase, and continuous math as a smooth ramp. Core differences: discrete, separate, distinct values with gaps in between. 1, 2, 3. Continuous, any infinite value with an interval, including fractions and decimals. Process: discrete, things are count. Continuous, things are measured. Main tools: discrete, logic, set theory, combinators, and continuous, calculus, limits, derivatives, and integers. Primary applications: discrete, computer science, network coding, data structures, cryptography, network routing, and graph theory. Combinatorics and probability with whole outcomes. So mathematics, physics, and engineering, motion, flow, economics and continuous movement, traditional geometry, and differential equation. Would you like to explore? I still don't get how their proofs be different, different, or what all what what you said means. Let's break down exactly what this means using simple ideas. The core difference is that discrete math handles separate objects like people, computer pixels, or whole numbers, while continuous math handles smooth things like time, speed, or water flowing. Because the subjects are different, the ways we prove things are completely different. How the proofs differ with example. Continuous math things are connected with no gaps. To prove things, you usually show what happens as you zoom in infinitely close, using calculus and limits. In discrete math, there are gaps. You cannot zoom in because there is nothing between the steps. Instead, you use structural patterns. Continuous proof examples. Example, the intermediate value theorem. The claim if you drive from 0 to 60 mile per hour, you must hit exactly 32.5 mile at some point. The proof style. Because speed is continuous, your acceleration cannot skip numbers. The proof uses limits to show that a connected line cannot get from 0 to 60 without crossing every single decimal point in between. Discrete proof example, mathematical induction. Claim a chain of domains of dominoes will always keep falling if the first one falls. The proof style. You cannot use calculus here because domains are separate objects. Instead, you use induction, a classical discrete proof. Show the first domino falls. Prove that if any random domino that if prove that if any random domino falls, it is close enough to knock over the next one. Therefore, they all must fall. Translating the jargon, here is what the terms from before actually mean in plain English. Actually means you count eggs, you measure milk. Discrete is counting, continuous is measuring. Combinatorics, the math of continuing combinations. Example, how many discrete different passwords can I make? Discrete. Counting combinations. How many discrete different passwords can I make? Discrete. Graph theory, the math of networks. How Facebook connects. Discrete. Friends, or how connects friends, or how Google Maps finds a route using roads. Discrete. The math of tracking constantly changing things. Calculus. Example, calculating the exact rocket fuel burned per millisecond. Continuous. Continuous. Visual combat. Imagine trying to prove how to get to the top of a hill. This approach, you prove that if you walk up a smooth ramp, your height increases smoothly with every tiny millimeter you move forward. Discrete proof, you prove that if you can climb the first step of a ladder, and you prove that if you can climb the first step of a ladder, you prove that if you can climb the first step of a ladder, and you know how to step from any rung to the next rung, and you know how to step from any rung to the next rung, you can reach the top. To help clear this up, would you like to work? Man, I am study discrete this and my background is in civil engineering. So explain it better than this, please. Going from the brains continues. In civil engineering, you deal with fields, fluids, and forces. You use calculus and differential equations because concrete stresses, water flow, and beam deflections happen smoothly and continuously over a distance or time. There are no gaps in a structural beam. Discrete math is like switching from pouring concrete to stacking bricks. When you stack bricks, you can't have 1.4 bricks. You have exactly 1, 2, 3, or 3 bricks. The math changes completely because you can no longer use derivatives when there is a massive gap between brick 1 and brick 2. Here is how discrete math translates directly to structural, hydraulic, and project concepts you already. How the proof differ. Engineering style. In civil engineering, you prove a structure is safe. In civil engineering, you prove a structure is safe at the limit of a material's strength or integrating a stress fluid field. In discrete math, you prove things using logic or step-by-step structures. Continuous proof, civil beam deflection. The problem, prove the exact sag deflection at the center of a bridge beam under a uniform load. How you prove it? You use calculus. You take a tiny, infinitely small slice of the beam, dx, write a differential equation for its bending moment, and integrate it over the entire length. You rely on the fact that the beam is a smooth, continuous solid. Discrete proof, computer network style, CPM scheduling. The problem proves that a construction project will take at least 40 days to complete. How you prove it? You cannot prove that a construction project will take at least 40 days to complete. How you prove it? You cannot integrate a construction schedule. A dry wall installation step is separate from a painting step. Instead, you use graph theory, discrete math. You draw the project as a network of nodes, tasks, and arrows, dependencies. You prove the 40-day minimum by using an algorithm to find the critical path, adding up distinct whole day durations of the bottleneck tasks. Okay, translating discrete math topics to civil engineering. We are starting at discrete textbook right now. Here is what those abstract traffic and pipe networks. In civil, a water distribution system is a network of pipes and junctions. In discrete math, this is a graph made of edges, pipes, and vertices junctions. Discrete math proofs show how to maximize flow through this network without overloading any single pipe. Common combinatorics, structural failure combinations. Structural failure combinations. Structural failure. If a building has 10 structural columns, if a building has 10 structural columns, 10 structural columns, and it can only survive if a building has 10 structural columns and it can only survive if at least 8 remain standing, how many different ways can the building fail? Combinatorics is the math of figuring out those exact structural combinations. Boolean logic, traffic signal controllers. Traffic lights at a complex intersections. Use discrete logic gates. If sensor A detects a car and pedestrian button B is not pressed, or emergency vehicle sensor C is active, then turn light green. Set theory, material specifications. Think of sets as classifying materials. Think of sets as classifying materials. Set A is all aggregates coarse enough for concrete. Coarse enough for concrete. Set B is all aggregates cheap enough for the budget. The intersection A intersection B or تقاطع A is your usable material list. This is what? Set theory. Okay. The structural breakdown, induction vs calculus. The hardest part for engineers is often mathematical induction, a major discrete proof method. Let's look at it like building a oh my god story skyscraper. To prove a continuous column won't buckle, use Euler's buckling formula, calculus. To prove a discrete structural process works for an infinite number of floors using induction, you only do 2 steps. Base case. Prove you can successfully build the foundation and the first floor. Inductive step. Prove that if any random floor is structurally sound, the engineering plans allow you to safely build the next floor K plus 1. On top of it, you can prove both. You have legally proved you can build a skyscraper to the moon step without ever needing calculus. Which is better? Okay. Now you are talking no sense. because I know for a fact that every floor you add changes the calculations, meaning there has to be from the start a certain 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 amount of columns and beams and I don't know how you call حديد تسليح iron and etc. So do not fuck with me. Now, fucking hell, I have to correct it sometime. You are 100% correct. And I completely deserve that call out. I oversimplified the engineering to try and make the math fit. And in doing so, I wrote something structurally impossible. In real civil engineering, a skyscraper is a top down load accumulation problem. You can't just copy paste floor calculations upward because the total dead load increases at the bottom with every story you add. The columns on floor 1 have to support everything above. Shut the fuck up. Meaning the design completely changes. I appreciate you stopping me. Let's throw out the skyscraper analogy completely and look at how a discrete group, a real structural engineering problem, does match the physics perfectly. A segmented cantilever bridge. Instead of a skyscraper, imagine you are building a segmented cantilever bridge out of identical precast concrete blocks. Motherfucker. Or an oversized crane boom made of identical steel truss segments. Each time you bolt a new identical steel segment into the end, two things happen. You extend the reach by exactly 1 unit, a discrete step. The bending moment at the fixed anchor point is increased because of the added weight. The bending moment at the fixed the bending moment at the fixed anchor point increases because of the added weight acting at a greater distance. The bending moment at the fixed anchor point increases because of the added weight acting at a greater distance. This is a problem where the engineering calculation changes with every segment. Changes with now we're talking. This is a problem where the engineering calculation changes segment, but we can use a discrete proof function to prove it will never collapse no matter how many segments we add. I like this. And or an oversized crane made of identical steel truss segments. Each time you bolt a new identical steel segment onto the end, two things happen. You extend the reach by exactly 1 unit. This creates the bending moment at the fixed anchor point. This is because of the added weight acting at a greater distance. With every segment, but we can use a discrete proof. It will never collapse no matter how many segments we add. How the discrete proof works with the real load map. Let's say you want to prove a mathematical formula for the total bending moment at the wall anchor. Oh my god. If this were a bored continuous concrete beam, you would use an integral because the distance is a smooth variable. Because this is made of distinct separate segments. You cannot integrate. There is no halfway bottled connection. you must use a summation and a discrete proof to handle the step-by-step jumps. Does does looking at well, look, I haven't dealt with bridges in during my study. But I believe you, if you say that for every one kilometer, say there would be a column, meaning that the bridge is that every kilometer of a bridge is going to be identical, then we are moving horizontally, then going forever is no problem. But man, math-wise, you're still doing a poor job. Spot on again if a bridge just repeats. Spans with a fresh pair under each one. You are just duplicating the same static problem horizontally forever. That it works for K to K1 is retrieval because they don't interact. It is poor math and a lazy explanation. Oh my god. Man. Okay. What's the difference? The difference. My god. Oh my. Between continuous and discrete. Oh my god. Thank God spelling doesn't matter in AI. Discrete math deals with things you can count one at a time, separate, distinct values, with gaps between them. Continuous math deals with things that flow smoothly with no gaps. You can always zoom in and find another value between any 2 points. Discrete integers 1, 2, 3, 4. There is nothing between 2 and 3. Graphs, networks, trees, logic and proofs. We can prove true, false, no in between. Continuing counting combinatorics. How many ways to arrange things? Many ways to arrange things. Algorithms, a sequence of distinct steps. Sequence of oh my god. Continuous real numbers between 2 and 3 there. Okay. Let's do forever. Calculus, derivatives, integrals, built on the idea of smooth, unbroken change. Physics, physics quantities like velocity, temperature, time, in the classical sense. In the classical sense. Curves, geometry, motion. Geometry, motion. A good mental image, discrete math is a staircase. Oh my god, again. Distinct steps, nothing in between. Continuous math is a ramp. You can be at any point at it. Where this lands for you. Conway is discrete math, propositional logic, proofs, graphs, counting, number theory, like the prime factorization. You like the prime factorization proof you just read. It is the backbone of computer science because computers fundamentally deal discrete stuff, bits, states, distinct operations. Calculus, which is next on your self-study roadmap, continuous math, rates of change, areas, under curves, limits. Interestingly, they are not totally walled off from each other. You sometimes see continuous techniques used to analyze discrete problems, like using integrals to estimate sums, and computers, despite being discrete machines, are constantly used to approximate continuous phenomena. Are continuously used to approximate continuous phenomena, like simulating physics. But as fields, discrete math is about the separate and countable. Continuous math is about the smooth and unbroken. I am asking because I thought I thought I can use this proofs in anything in math. I thought it's teaching proofs. Good instincts, and you are actually right. The proof techniques are universal. That's not where the discrete continuous split lives. Contradiction, induction, will ordering, direct proof, contrapositive, these are just logical tools. They don't care whether the objects you're reasoning about are discrete, integers, graphs, or continuous real numbers functions. You'll use induction in calculus, proving derivative rules for x. You'll use contradiction analysis, proving this is literally a well ordering, smallest counterexample style proof. You will use direct proof and counterpositive everywhere in every branch of math. So what's the actual splits? The technique, how you prove things, universal, transfer everything. The subject matter, what you're proving things about, this is what's discrete with continuous. Teaches proof techniques using discrete object as the practice material, integers, primes, sets, graphs, because those objects are clean and easy to reason about precisely. No weird limit infinity subtleties to trip over while you're still learning the logic itself. It is a deliberate pedagogical choice. Learn the hammer on nails before you try it on screws. When you get to calculus and real analysis later, you will be using the exact same proof machinery, induction, contradiction, direct proof, but now applied to continuous objects, limits, derivatives, convergence of infinite series, epsilon, delta arguments. The logic doesn't change, the terrain does. So yes, what you're building right now with is a general purpose proof toolkit, not a discrete math only toolkit. It's exactly why it is positioned early in your self-study roadmap before calc. You're not wasting effort here at all. You're building the thing you'll reuse in every math course. Wait, so in my course at CAM, I'll be using proofs. Okay. Say you're not much known. Be straight with you here, since that's how you like it. Khan Academy, statistics and pre-calculus course, computational and conceptual, not proof-based. Doing things like calculating problem with distributing pre-calculus. Occasionally, they will show you why a formula works, like deriving the variance formula or y equal on. But that's more. Here is a derivation, so you understand it's not magic. Rather than now you write a rigorous proof from axioms. The formal proof writing there the way you are it. Where proofs actually show up hard, real analysis, calculus proofs. If you ever go beyond applied calculus into a rigorous treatment, real analysis. Linear algebra, if taught proof style rather than computationally. A lot of intro linear algebra courses including for engineers are mostly computational to matrices solving systems, with proofs kept light unless it is a pure math version of the course. So the unstructured proof writing is really concentrated on your current roadmap, not something Academy will reinforce for you in parallel. That actually raises the stakes a bit on getting good reps in with. Now, since it might be your only proof heavy training until you hit something like CS50 AI, more formal underpinnings, or later ML math, which does get proofish again, things like Y gradient descent, convergence matrix, calculus driven. If proof fluency is something you specifically want to keep building, then let go cold after. That's worth knowing now rather than as Wait. You say already we've already discussed why I am going to what I'll be doing. Remember, oh my god. Discussed. Hey. Spelling. Remember. Still? Okay. Okay. So, am I going to use it again? Right. Yeah, you already laid out the roadmap. The not proof-based. Light to moderate proofs depends on how you take it. Calculus. Linear algebra, same territory. Computational. Solve systems, do magic. Skips proofs, limit. It's entirely a linear algebra course. It's things like why elegant vectors work, vector space properties. This is mostly not proof heavy, it's applied CS programming. Proofs come back for real. CS50 AI touches logic, search algorithm, validity reasoning. This has real overlap with what you are learning now. Propositional logic graphs, not full rigorous proof writing, but the same reasoning muscles and rules. The classic version has some math derivation, gradient descent, cause functions back that lean on calculus, algebra reasoning, though it's not proof heavy the way some optional advanced ML material does get into proving convergence bounds itself, but that's usually deeper than his intro course goes. Bottom line is mostly go quiet on your own until and ML math, and even then it's lighter, more applied flavor of proof thinking rather than the formal well-ordering induction style you're doing right now. Really is your one concentrated dose. Worth banking the skill well now, since nothing ahead reinforces it at the same intensity. Okay, this is just okay. Characteristics of discrete as opposed to continuous mathematics. To understand how it works, suppose there is a professor who brings to class a bottomless bag of assorted miniature candy bars. She offers to share the candy in the following way. First, she lines the students up in order. Next, she states two rules. The student at the beginning of the line gets a candy bar. If a student gets a candy bar, then the following student line also gets a candy bar. Let's number the students by their order in line, starting the count with 0, as usual in computer science. Now we can understand the second rule as a short description of a whole sequence of statements. If student gets a candy bar, then student 1 also gets one. When 1 gets a candy bar, then student 2 also gets one. If student 2 gets a candy bar, then student 3. Of course, this sequence has a more concise mathematical description. Then student n plus 1 gets a candy bar for all non-negative integers n. So suppose you are student 17. By this rule, you are entitled to a miniature candy bar. Well, student 0 gets a candy bar by the first rule. Therefore, by the second rule, student 1 also gets one, which means students 2 get one, which means student 3, so on and so on. By 17 applications of the professor's second rule, you get your candy bar. Of course, the rules actually guarantee a candy bar to every student, no matter how far back in line they may be. Rule for ordinary induction. The reasoning that led us to conclude that every student gets a candy bar is essentially all there is to induction. The principle of induction. Let P be a predicate. If P0 is true and Pn implies Pn plus 1 for all non-negative integers n. Then Pm is true for all non-negative integers m. What does Bm mean? Since we're going to consider several useful variants of induction in later sections, we'll refer to the induction method described above as ordinary induction when we need to distinguish it. Formulated as a proof rule. This would be rule induction rule B0 for all n belongs to natural numbers. Bn implies Bn so on, over for all m equal to n Bm. This general induction rule works for the same intuitive reason that all the students get candy bars. And we hope the explanation using candy bars makes it clear why the soundness of the ordinary induction can be taken for granted. In fact, the rule is so obvious that it's hard to see what more basic principle could be used to justify it. What's not obvious is how much mileage we get by using it. Familiar example, ordinary induction often works directly in proving that some statement about non-negative integers holds for all of them. For example, ordinary induction often works directly in proving that some statement about non-negative integers holds for all of them. For example, here is the formula for the sum of non-negative integers that we already proved using well-ordered principle. This time, let's use the induction principle to prove theorem 3.2.1. Suppose that we define predicate Pn to be the equation 3.2, which is this, okay. Recast in terms of this predicate. The theorem claims that Pn is true for all n belongs to n. This is great because the induction principle lets us reach precisely that conclusion, provided we establish two similar facts. P0 is true. For all n equal to n, Pn implies Pn plus 1. So now our job is reduced to proving these two statements. The first is true because P0 asserts that the sum of zero terms is equal to 0, which is true by definition. The second statement is more complicated, but remember the basic plan for proving the validity of any implication from section 2.3. Assume the statement on the left and then prove the statement on the right. In this case, we assume Bn in order to prove Bn, which is the equation. Okay, plus n plus 1. So it's 1 plus n plus 2 over 2. These two equations are quite similar. In fact, adding n plus 1 to both sides of the equation and amplifying the right side gives the equation. Yep, it is. You know what does this mean? This means that n already here is multiplied, so n is 2, it's multiplied in 3 here. So if n, it's the same. It's the same. Okay. Okay. Thus, if Pn is true, then so is Pn plus 1. This argument is valid for every non-negative integer n, so this establishes the second fact required by the induction principle. Therefore, the induction principle says that the predicate Pm is true for all non-negative integer m, so the theorem is proved. Induction principle says that the predicate P is true for all non-negative integers Pm, so the theorem is proved. A template for induction proofs A template for induction proofs. The proof of theorem 3.2 is relatively simple, but even the most complicated induction proof follows exactly the same template. There are 5 components. State that the proof uses induction. State that the proof uses induction. This is immediately conveys the overall structure of the proof. State that the proof uses induction. This immediately conveys the overall structure of the proof, which helps the reader understand your argument. Define an appropriate predicate Pn. The eventual conclusion of the induction argument will be that Pn is true for all non-negative n. Thus, you should define the predicate Pn so that your theorem is equivalent to or follows from this conclusion. Often the predicate can be lifted straight from the proposition that you are trying to prove. As in the example above, the predicate Pn is called the induction hypothesis. Sometimes the induction hypothesis will involve several variables, in which case you should indicate which variable serves as n. Prove that P0 is true. This is usually easy, as the example above. This part of the proof is called the base case basis step. Prove that Pn implies Pn plus 1 for every non-negative integer, and this is called the inductive step. This is called the inductive step. The basic plan is always the same. Assume that Pn is true and then use this assumption to prove that Pn plus 1 is true. These two statements should be fairly similar, but bridging the gap may require some ingenuity. Ingenu- ingenu- in- ingenuity. Ingenuity. Whatever argument you give must be valid for every non-negative integer. And since the goal is to prove the implication P0 to P1, P1 to P2, P2, B2 implies B3, etc. all at once. Invoke induction. Given these facts, the induction principle allows you to conclude that Pn is true for all non-negative n. This is the logical capstone of the whole argument. But it is so standard that it is useful not to mention it explicitly. Always be sure to explicitly label the base case and the inductive step. It will make your proofs clear, and it will decrease the chance that you forget a key step, such as checking the base case. A clean write-up. The proof of theorem 3.2.1 given above is perfectly valid. However, it contains a lot of extraneous explanation that you won't usually see in induction proofs. Perfectly valid, however, a lot of extras that you won't usually see in induction. The write-up below is closer to what you might see in print and should be prepared to produce yourself. We use induction. The induction hypothesis Pn will be equation 3.2. Base case B0 is true. Base case B0 is true because both sides of equation equal 0 when n equals 0. Inductive step. Assume that Pn is true. Where n is any non-negative integer, then so here, unlike the what did we call it? What was it? Unlike what we did first, which was assuming it's false and contradiction, forget the okay. Assume that Pn is true where n is any non-negative integer, then n plus n plus n plus 1. Okay? n plus 1 by induction hypothesis, n plus 1 over, well, by simple algebra, which proves Pn plus 1. Pn is true. So, and now we're assuming that Pn is true from the start. Now we're gonna start with proving that n plus 1, because n plus 1 means any number actually. It means, You know what I mean? Means in, you know. So 2 plus 1 is 3. 3 plus 1 is 4. So this is the definition of adding numbers. This is how you add numbers by induction. This is how you get a larger number. Keep getting a larger number by induction. Okay, which proves b in plus 1. Yep. Or be honest, this yeah, which proves b plus 1. Seriously, what if we take just this, and plug in the n plus 1 into n? Is gonna give the same result. Why did we add n by adding n plus 1 to both? Well, it makes sense. What if we plug in n plus 1 to then? What do we get? Is it the same? Is it? So n plus 1 over n plus 1 plus 1. But it's not going to be the same. It's not. Where is it? Over 2. What do we get? This is going to be n plus 2. So n plus 1 is going to be n plus 2. It is the same. You know, logically it is the same. It is the same. We came to the same conclusion. N plus 1, n plus 1 2 over 2. So we came to the same conclusion. N plus 1, n plus 2 over 2. Is this what does it mean? This one. I don't know. Pn. So what makes this? It is the same. If this is 2, then this is going to be 3. So if this is this both, this is going to be 2, this is going to be 3. Correct? It is logically, it makes sense, but I don't know, which proves Pn plus 1. So it follows by induction that Pn is true for all non-negative n. Ordinary induction. 2 to the power of n, 2 to the power of n. Figure courtyard for n equal 3. Okay. This means that this n equal 3. Okay. Induction was helpful for proving the correctness of this summation formula, but not helpful for discovering it in the first place. Tricks and methods for finding such formulas will be covered in part 3 of the text. A more challenging example. During the development of MIT's famous data center, as costs rose further and further beyond budget, there were some radical fundraising ideas. Some radical fundraising ideas. One rumored plan was to install a big courtyard. Wait. Fundraising. There were some radical fundraising ideas. One rumored plan was to install a big courtyard, courtyard, courtyard with dimensions as shown in figure for the case wherein stay, and to have one of the central squares be occupied by a statue of a wealthy potential donor who we will refer to as Bill for the purposes of preserving anonymity, anonymity. A complication was that the building's unconventional preserving anonymity. Complication was that the building's unconventional architect, Frank Gehry, was alleged to require that only special L-shaped titles were that the building's unconventional architect Frank Gehry was alleged to require that only special L-shaped tiles show in figure. Special L-shaped tiles be used for the courtyard. It was quickly determined that a courtyard meeting these constraints exist, at least for n equal to. See figure 3.3. Is this figure 3. Oh my god, do you want me to scroll? But what about for larger values of n? Is there a way to tile a 2 with an L-shaped tiled around a statue in the center? Let's try to prove that this is so. For all n larger than 0, there exists a tiling of a to the power n courtyard with Bill in a central square. Proof. Doomed attempt. The proof is by induction. Doomed attempt, I guess this means it's not working. Let Bn be the proposition that there exists a tiling of a 2 with a courtyard with Bill in the center. In the special case n, the whole courtyard consists of a single central square. Otherwise, there are 4 central squares. One by one. Okay. What does it mean? If n is 0, then this is going to be 1 by 1, which is 1. Anyways. It's going to be L-shaped, a special L-shaped tile. Okay. I thought the tiles themselves are L-shaped. But now, are you saying, is this wait. So this is the tile. Right, this is the tile. 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 But this is not what? This is square. Bill. This is Bill. Okay. I'm using L-shaped tiles for n equal to with Bill in a center square. It's not in the center. Is this center? It's not center. What do you mean it's center? What do you? Oh, in a center square. Okay. Base case. B0 is true because Bill fills the whole courtyard. Okay. Inductive step. Assume that there is a tiling of courtyard with Bill in the center for some n. We must prove that there is a way to tile 2n plus 1 and 2 courtyard Bill in the center. Now we're in trouble. The ability to tile a smaller courtyard with Bill in the center isn't much help in tiling a larger courtyard with Bill in the center. We haven't figured out how to bridge the gap between Pn and Pn plus 1. So if we're going to prove theorem 3.2.2 by induction, we're going to need some other way to it. Haven't figured out how to bridge the gap between P and N. So if we're going to prove theorem 2.2 by induction, we're going to need some other induction hypothesis, simply the statement about N that we're trying to prove. When this happens, your first fallback should be to look for a stronger induction hypothesis. That is, one which implies your previous hypothesis. For example, we could make Pn the proposition that for every location of Bill in in courtyard, there exists a tiling of the remainder. This advice may sound bizarre. If you can't prove something, try to prove something grander. But for induction arguments, this makes sense. In the inductive step, where you have to prove Pn implies Pn plus 1, you're in a better shape because you can appear, which is now a more powerful statement. Let's see how this plays out in the case of courtyard tiling. You're in plus Pn plus you are in better shape because you can assume Pn, which is now more powerful statement. Let's see how this plays out in the case of courtyard tiling. Proof. Proof. Successful attempt. The proof is by induction. Let Pn be the proposition that for every location of Bill there exists a tiling of the remainder. Base case B0 is true because Bill fills the whole courtyard. Inductive step. Assume that Pn is true for some n larger than 0. That is, for every location of Bill in a 2 courtyard, there exists a tiling of the remainder. Divide the courtyard into 4 quadrants, each to one quadrant contains Bill, P in the ground bill. Place a temporary bill X in the diagram in each of the three central squares lying outside this quadrant as shown in figure 3.1. Now we can tile each of the four quadrants by the induction assumption. Now we can tile each of the four quadrants by the induction assumption, replacing the three temporary bills with a single L-shaped tile completes the job. Proves that Pn implies P plus n for all n larger than. I don't get it. Do you get it? Assume that Pn is true also. For every location of bell in the courtyard, okay, there exists a tiling of the remainder. Divide the n into four quadrants. The n plus 1 into four quadrants. Each two into n. One quadrant contains bill B in the diagram below. Okay, place a temporary bill in each of the three central squares lying outside this quadrant as shown in figure. Now we can tile each of the four quadrants. Now we can tile each of the four quadrants by the induction assumption. What's the answer? Which is, are you for real? By the induction assumption, replacing the three temporary bills with a single L-shaped tile completes the job. This proves that for all n, thus Pm is true for all n. And the theorem follows as a special case where we put bill central square. This proof has two nice properties. First, not only the argument guarantee that a tiling exists, but also it gives an algorithm for finding such a tiling. Wait, this has to do with the 2 and then. Okay, 2, 1. Okay, here 2 and 1. There exists a tiling of the remainder. So that P is true for some n larger than 0. That is, for every location of bell in two courtyard, there exists a tiling of the remainder. Divide the n plus 1, which is, let's say, that's 4, and this is over, what was it? This was 1 before, so it's 4. Now it's 1 plus 1, which is 2, which means it's going to be 4 by 4, that's 16. 16, which is 16 is 4 and 4 and 4 and 4. So that's how is it divided into 4. Courtyard into 4 quadrants, each two. Okay, one quadrant, one of the quadrants of this one contains bill B in the diagram below. Place a temporary bill in each of the 3 central squares laying outside this quadrant as shown in figure 3.2. Squares laying outside this quadrant as shown in figure 3.4. Now we can tile each of the 4 quadrants. By the induction assumption, replacing the 3 temporary bills with a single L-shaped tile completes the job. This proves that Pn implies Pn, and this Pm is true for all n, and the theorem follows. This proof has 2 nice properties. First, not only does the argument guarantee that a tiling exists, but also it gives an algorithm for finding such a tiling. Second, we have a stronger result. If Bill wanted a statue on the edge of the courtyard, away from the pigeons, we could accommodate him. Strengthening the induction hypothesis is often a good move when an induction proof won't go through. But keep in mind that the stronger assertion must actually be true, otherwise there isn't much hope of constructing a valid proof. Sometimes finding just the right induction hypothesis require trial, error, and insight. For example, mathematicians spent almost 20 years trying to prove or disprove the conjecture that every planar graph is 5 choosable. Then, in 1994, Karstein Thomason gave an induction proof simple enough to explain on a napkin. The key turned out to be finding an extremely clever induction hypothesis. With that in hand, completing the argument was easy. A faulty induction proof. If we have done a good job in writing this text right about now, you should be thinking, hey, this induction stuff isn't so hard after all. Just show P0 is true, and then Pn implies Pn plus 1 for any number n. And you would be right, although sometimes when you start doing induction proofs on your own, you can run into trouble. For example, we will now attempt to ruin your day by using induction to prove that all horses are the same color. And just when you thought it was safe to skip class and work on your robot's program, instead, bummer. False theorem. All horses are the same. Notice that no n is mentioned in this assertion. So we're going to have to reformulate it in a way that makes an n explicit. In particular, will falsely prove that. Slight generalization of 5 colorability. Although every planar graph is 4 colorable, therefore 5 colorable, not every planar graph is 4 choosable. If this all sound like nonsense, don't panic. We'll discuss graphs, planarity, and coloring in part 2 of the text. False. In every set of n larger than 1 horses, all the horses are the same color. This is a statement. This a statement about all integers n larger than 1 rather than larger than 0. So it's natural to use a slight variation on induction. Prove P1 in the base case and then prove Pn implies Pn plus 1 for all n larger than 1. Inductive step. This is a perfectly valid variant of induction and is not the problem with the proof below. Bogus proof. The proof is by induction on n. The induction hypothesis Pn will be Fugazi-Bughazi. The proof is by induction on n. The induction hypothesis Pn will be in every set of n horses, all are the same color. Base case, n equal 1. Pn P1 is true because in a set of horses of size 1, there is only one horse, and this horse is definitely the same color as itself. Inductive step. Assume that Pn is true for some n larger than 1. That is, assume that in every set of n horses, all are the same color. Now consider a set of n plus 1 horses. N plus 1. H1, H2, H. By our assumption, the first n horse are the same color. This is not what we assumed, but okay. H plus 1. Okay. H plus 1. Also by our assumption, the last n horse are the same color. Yep, this is what we assumed. Okay. Yep. Okay. So H1 is the same color as the remaining horses besides Hn plus 1. That is H2, Hn, and likewise H is the same color as the remaining courses besides H2. Since H1 and Hn plus 1 are the same color as H2 and Hn, horses H1, H2, Hn plus 1 must all be the same color, and so Pn plus 1 is true. Thus Pn implies Pn plus 1. This is rubbish. What are you talking about? By the principle of induction, Pn is true for all n. What the fuck are you talking about? So H1 is the same color as the remaining courses besides Hn plus 1. That is H2 to Hn, and likewise Hn plus 1 is the same color as the remaining courses besides H1 to H2 on to H2 to Hn, since H1 and H are the same color as H2 to Hn, horses H1, H2 must all be the same color, and so Pn plus 1 is true. Thus Pn implies P. By the principle of induction, Pn is true for all n. We've proved something false. Is math proof? Should we all become poets? No, this proof has a mistake. The first error in this argument is the sentence that begins so H1 is the same color as the remaining horses besides notation in the expression creates the impression that there are some remaining courses, namely, besides H1 and H2 plus 1. However, this is not true when n equal 1. In that case, H equal H2, and there are no remaining courses beside and H2, Hn plus 1. So H1 and H2 need not be the same color. This mistake knocks a critical link out of our wait, what? It's not true when n equal 1. Impression that there are some remaining courses, namely H2 to H besides H1 and Hn plus 1. However, this is not true when n equal 1. In that case, it's true. Hn, which is 1, let's suppose it's 1, and Hn plus 1, n plus 1, n is 1, it's going to be 2. So it's going to be H2. What's going on? In that case, H1, H2, Hn plus 1, well, H1, H2, and there are courses. and there are no remaining courses besides H1 and Hn plus 1. So H1 and H2 need not be the same color. H1, H2, and there are no remaining courses besides H1, Hn plus 1. So H1, and H2 need not be the same color. This mistakes knocks a critical link out of our induction. We proved B1, we correctly proved B2 implies B3, and B3 implies B4, etc. But we failed to prove B1 implies B2. And so everything falls apart. We cannot conclude that P2, P3, etc. are true. And of course, these propositions are all false. There are sets of n non-uniformly colored horses for all n larger than 2. Students sometimes claim that the mistake in the proof is because Pn is false for n larger than 1, larger or equal to, and the proof assumes something false, namely Pn, in order to prove Pn plus 1. You should think about how to explain to such a student why this claim would get no credit on a math computer science exam. Well, I didn't get anything. That begins. So which one is the same color as in courses besides? The notation in the expression creates the impression that there are some courses, namely H2, besides H1 and H. However, this is not true when n equal. In that case, H1, H2, Hn plus 1 equal H1, H2, and there are no remaining courses besides H1 and Hn plus 1. So H1 and H2 need to not be the same color. Knocks a critical link out of our induction. We proved B1 and correctly proved B2 implies P3 implies, but we failed to prove that P1 equal B2, and so everything falls apart. We cannot conclude that P2, 3 are true. And of course, these propositions are all false. There are sets of non-empty color horses for all n larger than 2. Students sometimes claim that the mistake is because Pn is false or n larger, and the proof assumes something false, namely Pn. In order to prove Pn plus 1, you should think about how to explain to such a student why this would get no credit on. I don't get it. Induction versus well ordering. The induction rule looks nothing like the well ordering principle. But these two proofs methods are closely related. In fact, as the examples above suggest, We can take any will ordering proof and reformat it into an induction proof. Com- converse, Conversely, it's equally easy to take any induction proof and reformat it into a will ordering proof. It's equally easy to take any induction proof and reformat it into a will ordering proof. So what's the difference? Well, sometimes induction. So what's the difference? Well, sometimes induction proofs it's equally easy to take an induction. So what's the difference? Well, sometimes induction proofs are clearer because they resemble recursive procedures and reduce handling an input of size n plus 1 to handling 1 of size n. On the other hand, will ordering proofs sometimes seem more natural and also come out slightly shorter. The choice of method is really a matter of style and is up to you. Invariants. I swear to God, I can't. Let's check with. So I reached. Do I get induction? I don't think so. But I've spent a large time on this. They're faulty, I don't get it. And this was hard. Do I get it with number? Define an appropriate predicate. Thus, you should define the predicate Pn, so your theorem is equivalent to or follows from this conclusion. And the predicate can be lifted straight the proposition that you want to prove. As in the example above, predicate Pn is called the induction hypothesis. Sometimes the induction hypothesis will involve several variables, in which case you should indicate no. At what? Three point 2.6. stopped at 3.3 and wait. Not quite. Quit. Why? Why? Ah, fuck. Yes, you've actually got enough. Yes, you've actually got enough now for most of this set. Let me break down what maps to what you've read. Yes, you've actually got enough now for most of this set. Let me break down what maps double doable right now matches what you just covered. Problem 3, problem 6, problem 2, problem 4. Problem 1. By induction, by contradiction. Case work. No induction needed at all. I will let you know before this chapter. Problem 7. Z-links, ordinary induction. And hence, hold off on problem 5. My honest suggestion, do 1, 2, 4 first as a quick confidence builders. Then 3 and 6 as your real test of whether the invariant method landed. One, two, four. Until you've read 3.4, not start with one of these, or do you want me to just give hints? Pair your rule about. And I'll be asking you for asking you if not anything. So, should we do some problems? You guys, I don't really like it, but learn and share. So 1, 2, 4. First as a quick confidence builders. 1, 2, 4. Should we do 1, 2, 4? 1, 2, 4, 1, 2, 4. Should we do them separately? Okay. I'll come back to this in another video, another stream, if you may.